In this video, we're going to discuss the topic of recursion, and what we've already discussed in class is the topic of iteration. And just to review real quickly, iteration is when we are creating loops that are going to fold a repetitive process down into a couple of lines of code, like for instance with a while loop or a for loop or a for each loop. But now let's discuss recursion and what it is, and you'll see that there is this iterative thing going on as well with recursion, but it is a little different. So recursion, I've put my own definition on the screen here, but it's a method that is calling itself, which we'll call the recursive case. And that recursive call is creating iteration. So it will also need something that terminates this iteration, and we're going to call that the base case. So let's look at an example in code that is different from what we did with our iterative loops. So I have this function called recursive function, and up here we've got the method header, and it takes a parameter called n, and n is an integer. Then down at the bottom of this function, I have this call to itself, but it's a little bit different in that it is taking the parameter that is passed to it and subtracting 1. So with each call to itself, n is getting a little smaller. And while it's doing that, every time that this method executes, it's testing if n is 0 yet. So let me take my highlighter and highlight this. So when n does equal 0, this will cause a terminating action. This is going to only run this side of the decision. So let's see how this executes. Let's go ahead and bring up Eclipse here, and I have a very simple class that's going to load in that recursive function. Let me go ahead and expand this out a little bit. So here's my main method. This is the first line that's going to execute. It just instantiates this class, and it's going to come up here to the constructor and say print a number or enter a number. It's then going to ask for that number and then pass whatever number I type into recursive function. So we're going to highlight this, and I'm going to put a line break on line 13 and just watch it execute. All right, so I'm going to fold this down a little bit. Go ahead and put our emphasis here on the screen. So there's recursive function, there's its call to itself, and right here is its base case. All right, so let's play it. All right, so here I have to enter a number. I'm going to put in 3, and up here we're going to see the call stack. Let me make this a little bit bigger. So you can see it executed the main method, so it instantiated itself. Then it went to the constructor, simple example, and then now I just put in line 14, which, let me zoom up here a little bit. I put in the number 3, so it moved on down to here, and we're finally inside of our recursive function. So it's testing, is the parameter that I sent, which was the number 3, equal to 0? No, it is not. So this condition is false, meaning that it's going to skip down to the else side of this condition, and it should execute line 17 and print recursive call, and then make another call to itself. So let's watch that. I'm going to push F5 on my keyboard and make it jump down. So it went from here down to here. Now I should see, after I push F5 again, it prints recursive call to the screen. But in here, if I hover over my variable, it says that it equals 3. It's also up here in my watch list. Let me go ahead and slide that over here. N is currently 3, so 3 minus 1 is 2. So my problem is getting a little bit smaller here the next time it runs. I'm going to go ahead and push F5, and here it is. It jumped right back up to the beginning of this function, and now it says 2 double equals 0, and that would be false. So 2 is not equal to 0. So again, it's going to run this side of the condition, which causes it to iterate back up to here. So let me go ahead and push this, and if I hit F5 one more time, it's going to put recursive call down here again. And there it does. But now this time it's 2 minus 1. So again, it's going to go back up test the base case, and still it's going to be not there yet, so we're going to go ahead and produce another execution. And finally, we have in our watch list n is 0. So if I hover over this, it's going to say n equals 0. So now this will be true. So this is going to cause our recursive function to terminate. So before we execute the final recursive call in this function, I just want to point out what's happening in the call stack up here. We are consuming memory resources up here by having to remember our recursive calls each time we execute this method. So if I would have passed in a larger number, say 100, this stack would be significantly larger and consume much more memory resources. And this is kind of a cost benefit of recursion. Recursion could be a very elegant way to perform some sort of process or procedure, but it could also be very expensive on our call stack. For instance, if I had used iteration here with just a for loop, or a while loop, I could have said I want the loop to iterate n times. It would make one call to that function and be done with it. Anything that can be done recursively can also be done iteratively. So you have options. So the obvious question to answer is, why should I use recursion, or when should I use recursion? Well, recursion does have some performance advantages in some situations. For instance, there's a sorting algorithm called merge sort where it would outperform other types of sorting algorithms such as bubble sort or selection sort, and it's the better way to go. It just does things quicker. But there are other situations where recursion is not the correct way to go because it causes your call stack to get too big. For instance, we made a Fibonacci sequence program, and one of the things that I showed you was that the iterative version performed better than the recursive version. So those are some examples of when it's appropriate, when it's not. So think of it this way: if it's a nested structure, you may want to experiment with recursion and see if it does well with it. If it's flat data or linear data, you're probably going to be leaning towards an iterative approach. So let's go ahead and execute our final statement here. We are stuck in our recursive call here. So if I just hit F5, it's going to hit its base case. The base case is now true. N does equal 0, and it's going to print done. So let me go one more line. It prints done, which means that this recursive function will stop executing itself. And that reaches the end of our constructor, the end of our instantiation, and therefore the program concludes. So a really common example of recursion is to calculate a factorial. And a factorial is the product of all of the integers between 0 and the number that we're trying to determine. For example, if I was trying to find factorial 4 down here, factorial 4 would be the product of every number between 0 and 4. So that's 1 times 2 times 3 times 4, which results in factorial 4 being equal to the number 24. So let's look at a pattern here that factorials create, and that will help us determine an algorithm for calculating a factorial. So factorial 2 equals 2 times 1. Factorial 3 is 3 times 2 times 1. And factorial 4 is 4 times 3 times 2 times 1. You can start to see a pattern emerge. And as a matter of fact, if we look down diagonally, we should start to see that each factorial is actually n times n minus 1 continuously. So if this is our formula moving forward, we can put that into a recursive function and get this type of result. So if I went to the 20th factorial, our numbers are going to get really big really quick. So knowing how to calculate a factorial, we could create a function that looks something like this, where we're going to pass in a number, and if it's 1, which is our base case, we are going to return 1. Otherwise, we have a recursive call down here, which is the number n times n minus 1. And that will repeat and give us a result after it finally determines the base case and goes back through all of its calls to factorial n minus 1. So just to demonstrate that, let's watch this calculate factorial 6 in debug mode. So I've put a breakpoint here on line 17 of the program, and I'm going to push play. And here you can see in the call stack we have a call to the main method, call to our constructor, and now we're in this method here. And of course n is 6, so if I hover over it says n equals 6. You can also see that in my watch list up here. And I'm going to go ahead and push F5, which 6 is not equal to 1, so we're running the recursive version of this decision, n times n minus 1, so this would be 6. We know this side of this return statement, but we don't know what calculate factorial is going to return. 6 minus 1 is 5, so we're passing into this function 5 for another recursive call. All right, so now you can start to see the stack grows. This is our second iteration. Now I'm going to get it down to our base case here. So now we're on our iteration where we've gone down to 1, and we've made 1, 2, 3, 4, 5, 6 calls to calculate factorial. And in this case, we can return 1. So I'm going to advance to line 19. It's returning 1. But as we do this, it now has to return a value to each of its calls in our stack. And that way it can calculate whatever we left over from our previous calls. And ultimately it will give us the factorial of 6, which should be 720. So let's go ahead and just watch our stack start to shrink up here as it goes back through those method calls, and then finally I'm returning back to where I've made the call to calculate factorial, and it prints out 720. Okay, so that is a simple example of how the factorial recursive call would look and how it operates. And finally, we have triangular numbers. A triangular number is the sum of all of the whole numbers, all of the integers between 0 and the number that we're trying to calculate. So down here with the blue dots, I have a visual representation of them, which shows you why they look like triangles and why they're called triangular numbers. And at the very bottom, I have the calculation that they're performing. So if I'm trying to find the first triangular number, of course there's 1, but if I'm trying to find the second triangular number, I would have 1 plus 2. So 1 plus 2, or you can see the little pyramid starting to form here, would equal 3. And if I'm trying to find the third triangular number, it's 1 plus 2 plus 3. So 1 plus 2 plus 3 equals 6. And then finally the fourth triangular number, 1 plus 2 plus 3 plus 4, would add up to 10. So this is why they're called triangular numbers, because they kind of look like a triangle, and this is how they're calculated down here. So because this little demonstration is so similar to the factorials, I want to use this as a problem for you to solve. So I'd like you to try to figure out how to transform the factorial example that I showed you earlier into a triangular number algorithm. So I'm going to go ahead and just run this so you can see what it would look like. I'm going to go ahead and push play. It would say enter a number, and if I entered in 10, it would look like this: 10 plus 9 plus 8 plus 7 plus 6, all the way down to 1. If I added all those up, it gives me a result of 55. So I have a recursive function that's very similar to the recursive function for factorials that would just give me this output instead. So that is your challenge at the end of this video, is to create a Java class that will calculate the sum of a number and give us the result in a console output.